In this section, we're going to be looking at something called parametric equations, which is going to be where we have a separate equation for the horizontal position x and the vertical position y. So you can see an example of this in this first problem right here. We've got one equation for the x, one equation for the y, and we've got a third variable that both of those are in terms of. That third variable, in this case t, is called the parameter. That's where we get parametric equations. And it's often going to be t. It's often going to represent time. So one of the reasons that we might want to use this idea of parametric equations with separate equations for x and y, our picture may be a rocket being launched into space. You might want to look at the height of that rocket separately from any kind of horizontal tilt that's happening in its launch trajectory. You might want to look at what the height is just based on the time, and then you also might want to separately look at kind of any tilt or sideways motion at the time. And the height and the tilt or the sideways motion might not even really be that related to each other. And so you would look at those separately. Horizontal and vertical motion aren't always directly related. Sometimes the vertical motion and the horizontal motion are kind of separate things that you would look at each of those in terms of the time as the time goes on. So that's a little bit why we might want to do this. Again, this chapter is all going to be just kind of different ways of representing things, different kinds of constructs. And so let's try to sketch one of these parametric curves. So just like anything else, if we want to sketch something and we're not sure how, well, we always go back to making a table. But for this one, it's not just going to be an XY table anymore. Now you have to do a TXY table. So your T is going to be your input. Your T is your independent variable. And now both X and Y are outputs. Both X and Y are dependent variables. X depends on T and Y depends on T. Now on this one, we're actually giving you a what we call parameter interval. We're giving you the values of T that we're going to use. And so we'll just put those values of T in the table. We're just going to plug those in. So I'm going to take -2, plug it into the x equation. So -2 squared is 4, 4 minus 4, that'll be 0. -1 squared is 1, 1 minus 4 is -3. Then 0 minus 4 would be -4. And then 1 minus 4, -3 again. And then 4 minus 4 is 0. And then 3 squared, 9 minus 4 is 5. And then just be really careful when you're finding the y, make sure you remember to use the numbers for t here. Ignore this x row for a second. When people are going too fast, not being careful, they'll slip and they'll take the x and plug it into this equation. So make sure you use these numbers here. So -2 divided by 2 is -1, and then -1/2, 0 over 2 is just 0, 1/2, 2 over 2 is 1, and then 3 over 2 is 3/2. So then when we want to actually sketch this, when we want to graph this, the t is going to kind of fall away. We're still going to sketch it in the normal, what we call the Cartesian plane. Just this normal xy plane right here with x-axis and y-axis. So we're going to kind of ignore the t right now, and all we're going to do is just look at the, okay, this is an xy point here. So we've got the point 0, -1, and we're just going to plot that point. The t is not going to matter for plotting that point at all. All right, and then over here, we're going to have the point -3, -1/2. We're just going to plot that xy point just like normal. X, comma, y points. Right, plotting it, we don't look at the t. We use the t to find the x and the y, but then we just plot these different x's and y's here. Right? So now I've got -4 is 0, and then -3 and +1/2, and then 0, 1. Notice this one would not be a function as we typically would look at it. We've got multiple x's with the same y, so that can be one reason that we might want to look at parametric equations as well. X is a function of t, and y is a function of t. This is a function here, and that's a function there. So we have this graph, this curve represented by a couple different functions, since there's no one function that could represent this set of points here. Um, just another reason why these might be useful here. And so then we can just connect the dots just like any other graph. And we wouldn't put arrows at the end, right? Because it starts at this t-value, it starts at this point, and it stops at this t-value. It stops at this point. So we have a starting and a stopping point. This one's not continuing on forever. Now, the one thing is with parametric equations, notice how I said that we have a starting and a stopping. There's kind of a direction here. Normal graphs are just kind of a set of points that they just sit there on the paper. There's no direction of motion. There's no direction at all. This one, we started here, and then this was the next t-value. This was there's kind of a direction of motion here, and so what we often do is put arrows along the graph to show what the direction of the graph is, that this one is the starting and that one is the stopping points. Okay, those arrows don't mean that the graph goes on forever. It's just showing the direction. All right, so why don't you try sketching the next one here. So notice this one, I'm not going to give you the parameter interval, so you're going to have to think of your own t-values. You get to choose what the good t-values are. Now you got to kind of think about it a little bit. Notice you're square rooting t, so make sure you get the first t-value. What's the smallest number that you can square root? What's the first number that you can pick for t that's going to work? No imaginary numbers here, right? So what's the first number that you could have for t? And then you need to think about some nice values for t. You shouldn't be using your calculator here. You should be able to do this without a calculator. And so we don't want ugly decimals. We want nice points that are going to fit exactly on these grid lines as best as possible, right? So like 2 is probably not a good value for t. Square root of 2, that's not, we could approximate it and roughly put the points there, but it would be an estimate. We want some nice exact points. So try to come up with at least 4 values for t, where you're going to get really nice exact points on this grid right here. All right, so you go ahead and give this one a try. Make a table. And that's how we always go back to sketching anything new. Just make a table, pick at least 4 numbers for t, and make them good ones. Make sure you get the first t, the smallest t that works, and then pick nice ones where you'll get nice numbers that fit on exact grid lines. Go ahead and give that a try. Right, and so your graph should have looked something like this. So the smallest number that we can square root is 0. Negative numbers would give us imaginary numbers, so we got to start at 0. And then we wanted perfect squares for t, were the nice numbers. Again, things like 2 and 3, those would give us ugly decimals, so we'd have to approximate. We wanted perfect squares to get nice exact values here. And notice this one has a starting point, but then it does continue on forever at the end there, so it's kind of half of an upside down parabola. And then we put those arrows along there to indicate direction. Now you actually can do this in your graphing calculator. So we want to know how to sketch these by hand, but it is also possible to do in your calculator. So normally when you go in your calculator to graph, you hit y equals, there's just a y equals, and that's it. If you go to mode, there's actually, you've been in function mode all this time, where y had to be a function of x. Well, if you look over there, par actually stands for parametric. So I'm in mode here, and if I use the arrows to go over to par, if I hit enter, well now if I hit y equals, now it's going to show you an x equals and a y equals. Right? So for x equals, I can say square root, and then so this button right here next to alpha, you've probably been using for x all this time. I wonder if you ever wondered why there's other things on that button right there. This button actually gives you the input variable for whichever mode you happen to be in. So when you were in function mode, the input was x, so this button gave you x. Now that you're in parametric mode, the input is t, and so if you hit this same button that you've been hitting next to alpha here, this button will give you t. All right? And then here you can do 1 minus t. And then if you hit zoom 6, that's kind of a little bit funky here. Um, they actually programmed Zoom Standard, Zoom 6 for parametric really, really poorly in the TI graphing calculators. So you never want to do just Zoom Standard for parametric. If you go into your window here, so one thing is they always default to only doing positive t values. That was fine on this one, because we did only want positive t values, right? But there's plenty of other graphs where that wouldn't be the case. So in general, when you're doing parametric, what I would do is I would make your Tmin be -10 and your Tmax be 10. And then t-step, so your calculator is not magic. To graph something, it basically has to make a table, just like you do. The t-step is basically what the spacing in its table is, in terms of how frequently it chooses numbers to plug in. So 7.5 would be way too large, right? You don't want to step by 7.5 in your table. So by default, I would do 0.1. Whenever you're doing parametric graphs in your calculator, don't do Zoom Standard. It's terrible. Go into the window, put Tmin is -10, Tmax is 10, and T-step is 0.1. And then if you punch in your own window, then you just hit graph. And that should look a little bit better. Okay. So let's see here. Let's go over to the second page. So let's look at, so you're going to get these kinds of problems fairly often here where it talks about a particle, particle traveling in the XY plane. So we're doing maybe quantum physics here or something like that. We'll do this a lot just so that we don't have to try to create really realistic things, right? Like, an airplane or a baseball or those types of things would travel in very specific ways that would kind of restrict us to what kind of equations we could give you. We'd have to really look at it carefully to make it realistic. So instead of spending all that time, we just say, oh, let's just make it a particle. Quantum physics. Particles can do whatever they want, move however they want. So we'll look at a particle traveling in the XY plane, and we give you its position at a time t. Based on these equations, right? And we want to find the time when it's at specific spots. Okay, so what if the x coordinate is 5? So what we're looking to do is we're looking to have the x, which is this equation, equal 5. So this right here is saying we want x equal 5. So let's just plug that into this equation here. Let's replace x with 5. So we want to solve 5 equals t cubed minus t. Well, that's a cubic equation. We know how to solve any quadratic equation. Cubic equations in general, those will be a little bit trickier. That has to be a calculator problem, right? Back in the beginning of the course, we said we could solve any equation in the world in our calculator. In chapter 2, we did some polynomial equations. Where to solve them, we had to start off in our calculator. We need to use our calculator here. Now here's the thing though, if you're in parametric mode, so we just did this graph in parametric mode, if you go into your calc menu, if you do second trace to get to the calc menu, a lot of that good stuff is gone, right? Parametric mode doesn't have calc 0, calc intersect, calc max, calc min, none of that. All that good stuff is gone in parametric mode. So we actually can't just graph this whole parametric set of equations in our calculator and do some sort of calc 0, calc intersect. We have to use a workaround because of how TI programmed their calculators. So the workaround is we got to go back to function mode. To make all this good stuff come back, I've got to go into mode, and I've got to go to function. And then if I do second trace calc, now all this good stuff is back. Now I can do calc 0 and calc intersect. Those were the ways that I could solve any equation in the world, right? So the thing is though, in function mode, right? Function mode was y equals, and then we had to have x's here. Well, that's not a big deal. All that means is just instead of having t's here, let's make them x's. Okay, so we're going to be in function mode. We're going to solve 5 equals x cubed minus x. And that was when we could use either calc 0 or calc intersect, whichever one you preferred. All right. So that was where you could either graph like y equals 5 and y equals x cubed minus x and do calc intersect. Or what I tend to do more often is just subtract the 5 over here, make it equal to 0. So x cubed minus x minus 5, and then we can do calc 0. So it's just back to solving any equation in the world in your calculator. Let's see, whoops, I have something else here that I forgot to turn off. All right. So any equation in the world we can solve in our calculator using calc 0 or calc intersect. Now it might look like it's 2 right there, but be careful. If I trace 2, it's not quite 2, right? Remember, always check that. If it seems like it's a nice answer, do trace and check and see if it actually is, and it's not. So we've got to do calc 0. So I can trace calc, the second option there, left bound, I could do something like 0 or 1, a right bound, 3, 4, 5, something like that. Hit enter again, and there's our solution. Right? Now our calculator says that x is 1.904, but remember we changed t to x. What my calculator thinks is x is really the t value, right? We know that x is 5. We knew we were trying to find x is 5, so this answer that my calculator gives me isn't the x, it's really the t. So t about equals that 1.904 that I just found. All right, why don't you go ahead and give that a try in this second problem here. So it's going to be the same idea. You're going to have an equation to solve. You're not going to be able to solve that in parametric mode in your calculator. You've got to be in function mode to solve an equation. And just pretend like you're in chapter P. Honestly, if it was chapter P back at the very beginning of this class, back in August or September, if I gave you this equation to solve, like if there was none of this particle stuff, none of this parametric stuff, and I gave you just that equation to solve back at the beginning of the class, I don't think you really would have batted an eye at the fact that there was a t right there. You wouldn't have really cared. You would have just been like, ah, it's an equation to solve. I'll stick it in my calculator. Who cares what letter it is? Not a big deal. Okay? So just pretend like you're still in chapter P for a minute then. Just it's a letter. It doesn't really matter. It's an input. It's a variable. It's an unknown. It doesn't matter what letter we use for that unknown. We can just solve that in our calculator. And then just the final answer, make sure you realize that's a value for t. All right, so go ahead and give that a try in this second problem here. All right, so you can check your answer right there. You should have gotten about 5.327. And so the idea again is go back into function mode and just type this here. This is the equation you want to solve. You've got y equals 7. You want y to equal 7, so we replace y with 7 in this equation right here. Replace y with 7. And then we just want to solve that in our calculator. Just change the t to x. Go into function mode, change the t to x. You could have graphed y equals 7 separately. I subtracted it over. And then once you've got that right there, you can just do calc 0. And if you do, let's see, I've got that turned off now. Well, anyway, you get the idea. Once you graph it, you can do calc 0. Calc 0 will give you that answer right there. All right, so now let's take a look at this right here. These we should be able to do without a calculator now, these problems down here. We want to find some times when a particle is at the origin. So still doing quantum physics here, doing advanced physics now. And we'll get a position given by parametric equations, the x and y. We want to know when it's at the origin. Well, the origin, what does that mean? The origin is what point? It's the point 0, 0. So it means x equals 0, and here's the key, and y equals 0. Both have to be 0. So when I look at this, I need this equation to equal 0, and I need that other equation to equal 0. So, well, we can solve these here. This would be t t minus 1 equals 0. So over here I get t equals 0 and t equals 1. Then over here, that's not too bad to factor. T plus 6, t minus 1. So t equals negative 6, t equals 1. So here's the question though. Is it all of these answers? Do I just kind of smash this all together, maybe draw one big box around all those answers? No. Okay. Again, the key is it has to be x is 0 and y is 0. Okay. When t is 0, x is 0. But take a look, if I plug in t equals 0, I would get y equals negative 6. This right here would give me the point 0 comma negative 6. Last time I checked, that's not the origin. The origin has to be 0 comma 0. That's a point on the y-axis, but it is not the origin. All right, so this one doesn't work. What I need is for x to be 0 and y to be 0. That only happens at t equals 1. So you're looking for a solution or any solutions that occur for both equations that you see in both spots. Okay, so here that's just that t equals 1. Again, it's key and both of those have to equal 0. So it'd be a similar thing down here. We need this to equal 0 and this one to equal 0. This one's pretty straightforward, the same kind of thing. T minus 2, t minus 6 equals 0, t equals 2, t equals 6. This one over here might look a little bit weird. The reason that you're going to see some stuff like this is I noticed in talking to some students that sometimes what they did was they were just setting the two equations equal to each other, which sometimes would work. Because if x equals 0 and y equals 0, that means that x does equal y. But of course, you could also have the point 1 comma 1. You could have the point 5 comma 5. If you're just setting x equal to y, then you're not necessarily finding just when it's 0, 0. But a lot of times that would work and that would give them the right answer. And so what I did is I created kind of some of these silly looking problems where it would be difficult for you to set these two equations equal to each other. That would be pretty complicated to solve, but it's not hard actually to solve each of them equals 0. If you take a look at this one here, we've still got the 0 product property. We still either have this part equals 0, which would be t equals 2, or we've got this part equals 0. Right? Well, if you want t plus the square root of pi to the 13.2 e to equal 0, that exponent's not going to matter. Right? If you want to get 0, the only way to do it is to have 0 to whatever exponent that is. So that means t plus root pi has to equal 0. So subtract the root pi. This one over here is t equals negative root pi. Okay. But really, this one's not going to matter. Whatever silly answer this is over here, we didn't have that silly kind of weird answer over here. We're just looking for anything that matches. T equals 2 shows up in both spots, and so the answer is just t equals 2. That's where x and y are both 0, and so it's at the origin.